I don't know why this transcription is always showing up. Anyway, all right. So hi everybody. So today we're gonna talk about magma degassing, and we're gonna have Echo that's gonna talk about mostly Sulfur X code. Just before that, I want to make just a few announcements. So I just uploaded the updating schedule for the class on Box. It's on the course material folder. And let me just share with you the Word document here. So we actually did a few updates on Monday about the second half of the class. It's going to be after spring break. So we are just right here on week 7. We're going to talk about magma degassing. And then next week we don't have any class because it's spring break here. So no class next week, next Monday. So then the following one is going to be on the March 20, and we're going to talk about progressive density currents and Lahar codes, probably mostly progressive density currents. And we're going to show you some examples of codes we have on Victor for that. Then after on March 27, we're going to have Mark Gioso. They're going to talk about MELS and the Anki portal. So I'm going to send you an email soon before that to actually create an account and logging into this Anki portal. So then you guys can actually do the activities with Mark on that day. So wait for an email from me probably after spring break to show you how to create an account on the portal. And then April 3rd, we were thinking about doing some activities about DEMs, digital elevation models, and raster tools. And then finally on April 10th, then we're gonna have a session on magma storage, and we have a guest, Wendy Borson, is going to talk about the magma chamber simulator. And that ends for the planned activities. So what we were thinking is that during the two last session we have on April 17th and April 24th, that you guys could actually present some projects you have, and we were thinking that maybe some of you already started using some of the codes on Victor for your projects. So we would really love to hear from you on that. And so if there's any volunteer that want to, you don't have to have like a lot of results, like, just, showing us what you want to do with Victor, which code you want to use, and what is your project, and how do you want to use Victor for your projects. That would be super cool. So either on the 17th or 24th, we would like to have these kind of activities. We were thinking also that we could, for some of you that want to, we could actually give you some little activities to do. We can actually give you, for example, a code and a workflow, and ask you to get some outputs from one of our codes that we have. So if you're interested in that too, that's something we can also plan during these last 2 weeks. So being a little bit more interactive and a little bit more about you doing leading the sessions rather than us for these 2 last weeks. Okay. So this is available on Box on the course material folder that I share. I can share the link again if you guys want. So that's for this schedule. And then the second announcement, I guess, is a workshop that we are tentatively planning to do in August. It's going to be, I think, the second week of August. That's what we said. Check the exact dates. Yeah, so the week of the 5th to the 9th of August. We're planning to do an in-person workshop at Columbia in New York, led by Enad. So we will really like you guys to participate. So we have some funding from an SF for that. So we can fund your travel, we can fund your accommodation. And so some of you that participated in this short course should be the primary ones that we would like you to come to actually work a little bit more on your projects and show you a little bit more of what we can do with Victor. So I guess maybe Anna and Sam, you guys are gonna send some announcement on the listserv probably, and there's gonna be a link to register for that workshop soon. Just keep posted.
And we're gonna tailor that workshop to the participants. So if it's more kind of new folks to the platform, it'll be more introduction. But if it's more people who have already had experience, then we can do more of a hackathon, either work on a project together or just do concentrated time for people to work and help each other.
Yep. So look at the email from the listserv, and then probably we can also put a link during this short course during the next sessions we're gonna do in the end of March. So then you guys can also have a link to register for those who are interested. Any questions so far? What we just said? Any comments or anything? Okay. All right. So I guess we can start with you, Echo, on magma degassing.
Sure. Okay, so how can I share? Oh, here we go.
Yeah, it's on the top right. Yeah.
Yeah. So screen. Here we go. Wait, which screen are you seeing? Are you seeing
the presentation mode, the presenter mode?
Presenter mode. How about now?
Yeah, that's good.
Okay, cool. Thanks. All right, cool. Well, hello everyone. I'm Echo. I am an associate research scientist at Lamont, and thanks for having me today. And thanks for implementing SulfurX on Victor. I think it's really cool, and it will really increase the accessibility of SulfurX to people. So thanks. So in today's presentation, I think we'll talk about volatile degassing during magma ascent. And so the flow of the presentation will be, first I will briefly introduce the mechanism, or briefly introduce the volatile degassing, including some of common approach like modeling and melt inclusion and experiments. And then I will briefly introduce the mechanism of CO2 water degassing and some of the commonly used models. And then the focus of today would be talking about the mechanism of sulfur degassing, and then how SulfurX works. And then lastly, I think I will just demonstrate how to run SulfurX on Victor, how, what are each input parameter, and how to interpret the results spreadsheet. Okay. Why it doesn't work? Okay, here we go. So I guess, first of all, when we talk about the volatiles in the magma, I think most of us are mainly thinking about water, CO2, and sulfur maybe, and some halogens. And so water, of course, is actually one of the most abundant volatiles in the magma. And they are present in like the level of weight percent. And then for CO2, sulfur, and chlorine, they're less abundant. But we are usually looking at about hundreds to thousands of ppm level in the magma. This also depending on like the stage of the magma we're looking at. And we care about these volatiles, of course, because these are essential elements that have played an important role, particularly in regulating like our surface temperature. For example, the atmospheric CO2 level affect the surface temperature in the long run over the geological time scale. And then for sulfur, volcanic degassing, releasing large amount of SO2 to the atmosphere that could cause short-term but very significant global cooling. but the existence of this magma in the magma itself can also affect our volcanic process, right? So, for example, the dissolved amount, the amount of water that's in the magma can affect the melt viscosity, and the formation of this vapor bubble. So the formation of this vapor bubble in the magma can definitely affect the magma compressibility and buoyancy. So this whole process, during magma ascent from high pressure to low pressure, and then bubble nucleation and then bubble growth can be modeled by some conduit model. I think one of our previous lectures actually talked about. But when we talk about degassing models, or what I want to talk about today, is really to describe during this vapor magma equilibrium, how do different volatiles behave. So here, the highlighted word is equilibrium. So basically, we are assuming so all these degassing models are assuming actually all the chemistry reactions have already reached equilibrium. So that's like the key. I think it's like the primary assumption here when you use this degassing model. So during this whole process, right, different volatiles actually behave quite differently. But one of the key concept here is volatile solubility. That really kind of decides at what pressure and how much different volatiles kind of exhaust from the magma and go into the vapor phase. And this solubility concept particularly applied very well to CO2 and water. I guess sulfur is slightly different, which I will talk about later. But so basically solubility is like the maximum amount of volatiles, like the maximum amount of CO2 or water can be dissolved in the magma. And it's actually very sensitive to pressure change. So one of the very common figure we will see when we talk about volatile behavior will be looking like this. So basically, X is the concentration of volatile, here is CO2, and then Y could be pressure or depth. And we would usually see a decreasing trend here because volatile solubilities in general decrease, or at least the CO2, water, and sulfur decrease as pressure decrease. And that's why the magma would be degassing during the magma ascent. Okay, so before we talk about modeling, there are actually another two approach people usually use to understand volatile behavior. And in fact, when we study volatile behavior, we could usually, like, the current trend is like people would combine all these different approach. So the other two approach would be, first is the looking at melt inclusion. So how do we really know how much volatiles are in the magma? If you measure the CO2 water concentration in the matrix gases or in the lava flow, those are typically already degassed, and they have very low volatile concentration. So we don't really know, like, at higher pressure, when the magma was in the conduit, how much volatiles can be there. So that's when we turn to this melt inclusion. So melt inclusion basically is this little melt puzzle, this thing kind of got entrapped inside a crystal during crystal growth. So and ideally, this melt inclusion would be kind of sealed in the crystal and preserve all the information about this magma at the time when it was entrapped, right? Including how much CO2, water, sulfur, and halogen the magma contained at that moment. So that is actually really cool because it can give us the information of the magma, but it can also be used to infer the pressure. It's because if we assume when the melt inclusion is actually entrapped, this magma was already volatile saturated. Then because the solubility of the volatiles, particularly CO2 and water, is sensitive to pressure. So we can use the CO2 water concentration in the melt inclusion to infer what is the pressure. And another thing is, just imagine if we kind of look at a lot of melt inclusions and they were likely to entrap at different pressure along this decompression path, then it will give us a record of the whole degassing process. And some of the melt inclusions could be even entrapped really, really early. And at that time, maybe the magma has actually experienced very little degassing. And then that melting inclusion would give us the initial content, or how much volatile that parental magma contains. So all these are really nice, like a very ideal, but it's an ideal case of using melting inclusion. So there are some assumptions. The first is, of course, we assume, again, this big condition is that we assume they actually reach equilibrium. And the second is the melting inclusion is really preserving the information at the time when it was entrapped. So there is no post-entrapment modification, which is usually not the case. So that's why it involves a lot of correction. And one of the big modification regarding to CO2 we will talk about later is this little vapor bubble inside the melting inclusion. But then the third request is actually we need to know very well how solubility change as a function of pressure, right? So in order to use the volatile or the CO2 water concentration to infer the pressure, we really need to know this relation really well. So how do we constrain this? And then this then comes to like another approach, which is very important in terms of both understanding the behavior and also construct any degassing model. Is we do high pressure, or not very high pressure, high temperature usually, but at different pressure experiments to kind of simulate the conditions. So there are several simulated conditions, and then really study the volatile degassing. So the common apparatus we will be using to study the solubility, volatile solubility would be, if it's 1 atmosphere, we can just use 1 atmosphere gas furnace. And then at high pressure, what we can use is internally heated pressure vessel, which looks like this. So this is like a gas median apparatus. So we would actually using argon gas as the pressure median. And this pressure vessel is actually really nice, probably the best apparatus to study volcanic process actually, because it covers pressure between between very low, like half kilobar to like 3 or 4 kilobar. So that's really what like usually volcanic process are happening. And then if someone is really interested in like higher pressure, like the lower crust or upper mantle level, one can use piston cylinder, which is showing here. And this is a solid pressure median apparatus. So using these different apparatus, we can go to different pressure as for interest. So what we do is we put like some certain known starting material like silicate glass, and then we add volatiles to it. So if you study only water, then you only add water. This can be added either as some hydrous mineral, for example, like brucite, or it can be also add just use a little syringe to add as a distilled water, like a free water place. And then if we want to say water and CO2, then we add water and some format of CO2. So one of the commonly used one is oxalic acid dihydrate. So basically it's like a compound containing both water and CO2. And then for sulfur, you can add as either sulfate, like calcium sulfate, either in solid or in solution. And you can also add iron sulfide in solid. So the key here is, because we're studying solubility, right? So we really want to add, so we have some idea of how much it can be dissolved, and we really want to add more than that to make sure the experiments are actually saturated by fluid. So in this way, we can talk about solubility by measuring, because the solubility basically is the maximum amount of the volatiles dissolved in the magma, right? So if we add more than that, and we make sure after the run there is a fluid phase present, then we know the experiments are saturated. So we can then, by analyzing the volatile content in the glass part, to know the solubility of each volatiles, like water and CO2. So the nice thing of conducting this kind of experiments is because we can really control all the variables. Unlike the melting inclusions, there are so many unknowns, right? You don't know if it's modified, you don't know what actually the pressure and the temperature of the magma. For doing experiments, we know all these things. And we know what's the pressure we're going to, we know what's the temperature of the experiments. We could start with a powder, like a silicate glass that we really know already characterized. We know the major elements, and then we know how much volatiles we started with. So then after doing the experiments, then we can really analyze. So the solubility would be how much is dissolved in a silicate glass, right? So for water and CO2, we can use FTIR or SIMS to analyze it. The nice thing of FTIR is actually you don't really it does not only tell you how much the amount of the water and CO2 in the glass, it also tells you the speciation. FTIR spectrum. So here you can see and this is a basalt. So you can see CO2 does not really exist as molecular CO2 in the basalt. It actually present as the carbonates here. And then for water, it can be both actually molecular water, which is shown here, and OH. That's what and so there is and so this big peak is the total water. So this really tells you the speciation. And why do we care about speciation in this case? It's because that really affects us how we later write the volatile dissolution formula, and it really determines how we model these solubilities of each volatiles. And then let's back to the experiments. So experiments does not only tell us the solubility, basically is how much is dissolved in the glass. It can also tell us how much it was actually present in the fluid phase. So if we know in total how much we put in the experiments, and the whole experiment is actually a closed system, so we could actually constrain how much volatile goes into the fluid by using mass balance, or using actually directed measurement by gravimetry. This is particularly good for water. So you basically puncture the experiments, and then puncture the capsule, and then you put the capsule into the oven and dry it, and then you measure the weight difference. Then you know how much water is there, because we're assuming CO2 and sulfur is minor amount, right? So CO2 can actually also measure by this same way, and you can use like the different temperature. So we know water present as ice in 0, but the CO2 I think is minus 80 degrees. So if you put a capsule into the liquid nitrogen first, then CO2 would become solid, and then you take it out. So both CO2 and water will be solid, and then you take it out and you puncture it immediately. So in that way, there's a weight difference. That's mostly would be CO2, because water would be still present as ice. So and sulfur then is trickier, because sulfur, later we'll see, sulfur does not really only go to the gas. It also can present as solid phase. So sulfur is a little bit more tricky when you do this kind of experiments. You really want to avoid formation of sulfate or sulfide mineral in the experiments. And because of this actually becomes one of the major error source of this kind of experiments to determine sulfur behavior, is because you could actually overestimate the amount of sulfur in the fluid. If you do not really carefully exclude, it could actually go to the sulfide or sulfate solid. Anyway, so these are all the information experiments can tell us. And again, and all these, we also know the pressure and temperature and the melting inclusion. So this really provides, like all these experiments provide really good information later we can use to calibrate our models. And oh yeah, there's another. So for sulfur, again, in the glass, we could measure it using electron microprobe, and that's very accessible to many institutions. And then for sulfur speciation, this is actually a major, a newer or a more recent technique. So before, we could tell the sulfur speciation in the glass using Raman or even using microprobe, but that can only kind of give us a qualitative estimate what kind of species, sulfur species was there, but it's really hard to quantify them. So then then there's this technique called X-ray absorption near edge structure, XANS, basically using a synchrotron to measure the sulfur speciation. So here's a picture of the XANS, the synchrotron in APS in Oregon National Lab. So this technique of enabling us to quantify different sulfur speciation in the magma, that really improved our understanding of sulfur degassing. And I think this is like a really big step, encouraged a lot more recent sulfur modeling, sulfur degassing modeling, including Sulfur X. Okay, so now, so there are a lot of experiments. Like I think since 80s, there are people started doing a lot of experiments, first on water only, and then water CO2, and then water CO2 sulfur. That's a little bit less, but yeah, so thanks to all these experiments, we kind of know. So of course, for water CO2 sulfur, pressure is a big player here, but pressure is not the only player. Then people started realizing, okay, temperature has an effect, but much less. And then melt composition actually matters a lot. So for example, basalt, andesite, and rhyolites, the solubilities are very different. And actually, for the record here, like Sulfur X and many of the many existing degassing models are actually best calibrated in the basalt and basaltic andesites range. And there are actually way less experiments focusing on andesite, like the intermediate composition. And for rhyolites, there are there are actually only a couple of degassing models can actually do the model for rhyolites. And then oxygen fugacity, and that's more for sulfur because sulfur is a multivalent element that I will talk about later. But anyway, so we know there are a lot of factors can affect in general affecting volatile solubilities. So the way we kind of model is first we write a formula, like basically to describe the mechanism of how each volatile is dissolved in the magma. And this can be very thermodynamic or can be very empirical. And that's why we want to know the speciation. It's because when we write chemistry reaction and write a formula, we really want to know what we are dealing with. And then in either thermodynamic or empirical, we need using all these experiments, right? With known pressure, temperature, and with known melt composition, know how much volatiles are dissolved and how much is in the fluid. Then we can use these experiments to calibrate our formula, either thermodynamic formula or empirical formula. So this is how usually, like when we study volatile solubility and how to model it. That's kind of the basic workflow here. And so now we can, is there any question actually? No? Okay, cool. So now we can go to each volatiles. So here I think I will give a kind of detailed, so first is water CO2. So here is an example about when I talk about the formula. So when we were talking about CO2 here, it's actually specifically for basalts. As I said, it's dissolved actually as carbonate here. So we can write a reaction like this. Okay, CO2 in the vapor plus some oxygen ion in the melt, and then forms carbonates ion in the melt. And then we can write the equilibrium constant of this formula. Okay, so the basic equilibrium constant we will see is the products of the products of the reaction at the top, and then at the bottom is the products of the reactants. That's like yeah, so that's how you write a equilibrium constant, and these squares basically represent the concentration. But when we talk about, so here is the equilibrium constant of these particular reaction. Okay, so here when we talk about concentration, it's really the effective concentration. So the effective concentration, we actually in thermodynamic we call it either activity or fugacity. If it's a gas phase, we call it fugacity. So here we can say it's the is the activity of carbonates in the magma at a certain pressure and temperature. Oh, and the equilibrium constant is related to the pressure and temperature. So it's the activity of carbonates in the melt divided by the activity of the oxygen ion in the melt times the CO2 fugacity in the vapor. That's the equilibrium constant. And then we can rewrite it in this formula. So then here the P0 and T0 is basically the reference pressure and temperature. This is kind of arbitrary. So but then the T and P here is the real pressure and temperature. So the delta V is basically the molar volume change of this reaction. So here is basically it's the molar volume change of the reaction. And then here we're talking about basically it's the carbonates, molar volume of the carbonates minus the molar volume of the oxygen ion. And then this is the delta H is the enthalpy change, molar enthalpy change of this whole reaction. So by doing this, we are basically expressing this equilibrium constant, right? The right side is actually a function of pressure and temperature with this delta V, delta R, and the K0. So these things we actually don't know. But for experiments, what can give us is the pressure and temperature, right? So these are the already, if we want to use the experiments to kind of calibrate, so then we know the pressure and temperature. And then so for some of the early models, they kind of do it in a simple way. For example, this Sulfur and Holloway, 1987 is actually one of the earliest CO2 water models. So they basically assume, it's so that the melt is actually an ideal mixture of carbonate and oxygen. So in this way, they basically they don't need to deal with activity anymore, because the activity is the product of it's the product of the concentration and the activity coefficient, right? So if it's actually ideal mixing, this activity coefficient would be 1. So here they just made an assumption, okay, it's ideal mixture. So the activity coefficient is 1. So instead of dealing with activity, we are dealing with actually really the concentration. And that's great, because again, this concentration, we can measure it, right? We can measure it from our experiments. So in this study, what they basically did is, okay, so these we can all measure. So the fugacity, instead of dealing with fugacity, we're dealing with the concentration, the molar fraction of CO2 in the vapor phase. So here is all molar, that's why it's X. Actually, that's also why sulfur X is called sulfur X, because the X means the molar fraction of each component. So all these we can measure in the experiment, right? That's the left hand of this, that's the K. And then the right hand is this, right? So it's pressure and temperature, and the reference pressure and temperature, you can give a reference pressure temperature. So in this way, so this study basically used a lot of experiments to and the least square to kind of regress for the unknowns. The unknowns is basically the K0, V0, and the H0. So then we got a formulation of the CO2 solubility. So that's how most, I mean, so then if we can look at a more recent model, it's actually the same idea. It's just so here they simplified activity coefficient here. And here they kind of try to deal with it more, in more detail, right? So it's the same equation. You write the K, you write the equilibrium constant, and then you have the enthalpy change, and you have the molar volume change. But then here, instead of just assume this, but then here, instead of assume the FCO2 it's just the, let me see here. Oh, yeah. So instead of assume is ideal mixing, so you don't have to deal with this gamma, which is the activity coefficient. Here they say, okay, the activity coefficient is actually a function of different composition in the magma. which that's the case, right? Because the carbonates is actually one of the components in the whole silicate melt, and it's not an ideal mixing, right? And here, instead of saying activity of the oxygen is just the, here they basically assume the oxygen is just whatever is not carbonates is oxygen. So here it really dealt with it. So in this Incarno-Marziano model, they say, okay, the activity of oxygen is actually a function of non-bridge. So this NBO over O is the non-bridging oxygen. Non-bridging oxygen is basically the oxygen that was not connected with the tetrahedral, like aluminum or silica. So that's a non-bridging oxygen. So because those are let's put it that way. Non-bridging oxygen is the oxygen actually is available to connect with other cations. If it was kind of bonded with aluminum and silicon, it's less available. So they think so that's how they kind of parameterize this thing. So then the whole equation, if we look at equation 7, it's actually very similar to our previous equation. Still have the pressure over temperature term. It has a 1 over T term, but it has another, and it also have the partial pressure. Here, the partial pressure basically is the pressure times the mole fraction of CO2. That's the partial pressure. So, but then, on top of that, we also have these two compositional terms. Basically to account for the activity. So it's so we can see here in this paper. So what the composition they are looking at is basically aluminum, calcium, potassium, and sodium, iron, magnesium. So it's true that for like the particular alkalines, because we know like CO2 existing in the magma as a carbonate. So it's actually preferred to combine to bind with alkaline cations like potassium and sodium and calcium. So that's why it makes sense that all this compositional term actually matters. So that's why it's actually there are more. Then later there are more models. For example, like this Incarno-Marziano models, their experiments are actually focusing on more alkaline rich magma. Because it actually really makes a difference here. And so for nowadays, like when people are doing solubility experiments, there are actually very few experiments only look at CO2 or only look at water. And the reason is because like they both exist in the magma, and they also can actually affect each other. So for this is again from Incarno-Marziano et al. 2012 paper. So we can see that how the water, the way they deal with it is actually the same way. So you have the water dissolved. So you write the equation. So for water is water to molecular water in the melt. But actually, water does not only exist as molecular water. It also exists as OH in the melt. So there are like two species. And then again. But here they assume, I think they assume everything is molecular water. So they write the equilibrium constant of reaction 8 like this. And then again, then you need the activity, taking account of the activity coefficient and the activity of oxygen cation here. And then they use NBO over O as the to calculate the activity of the oxygen cation, and then using other oxides to account for the activity coefficient of OH here. Oh yeah, I think they deal with only OH here. I think that's how it goes. So it's only the OH activity coefficient of OH and activity and the mole fraction of OH in the equation. So I just mentioned this how like this is one figure people will very often see when we talk about water and CO2. So basically, water concentration in the magma would be in the x-axis and CO2 in the y, and the way people would so for you when we study melting inclusion, we would measure, okay, what is the water concentration and what is CO2 concentration. And then because water CO2 solubility are very sensitive to pressure, and then what all these existing water CO2 model can do is actually to calculate with a given water CO2 concentration, and assuming that magma is actually fluid saturated, then it can give you what's the pressure. So that's how we actually calculate the pressure, how we infer the pressure using water and solubility. But then the thing is, there are already several models, right? Naturally, we will think about, oh, how do different models compare? So this work was done in 2012, and there are like several pretty commonly used CO2 water degassing model. And we can see each line. So the solid lines is Incono-Marziano model, and then the thin solid line is volatile calc, is another like very classic, commonly used model. And then this dashed line is the Papale et al. Model. It's another more thermodynamic and vigorous model. But we can see that, okay, well, at 1 kilobar, they sort of agree, and 2 kilobar, 2 kilobar, they already started to kind of diverge from each other. And particularly what you notice is that the shape of this line, right? So it also changed. So at certain pressure, in general, if the magma is very enriched in water, the CO2 solubility would be lower compared to if it's a drier magma. But then this line, the shape is actually started changing too. For example, the Papale model, right? This is like concave up at this low water part. And then for other two models, it's actually concave down. And then the discrepancy of this pressure, predicted pressure, actually gets bigger and bigger when the pressure it actually gets higher. I think one of the reasons is because most of this empirical model just assume CO2 and water is an ideal mixture in the fluid. But as the pressure gets higher, the non-ideality actually become more obvious, affecting the CO2 water behavior. But another thing is most of the experiments, like the experiments are done at higher pressure or much less. So that's another thing we need to take into account when we look at these models. Okay, so there are actually, so I just kind of talked about, focus on one and talk about the other two, but there are actually a lot of CO2 water degassing model right now. But the nice thing is there is actually a review paper and a program, kind of a platform, kind of actually had a lot of most of these models available, and it's written in Python. It's called Vesical. So there are the paper is in two parts. The first part is basically describe Vesical, and the second part is actually they're trying to benchmark all these models. And the Vesical, so if you are really interested in the CO2 water degassing model, you could go to read this paper. And the Vesical is also it's written in Python, and it's available on Anki. I think it's the same Anki that Mark he also will talk about later. So yeah, so that's the water and CO2 model. Any question? Good, cool. Okay, let's talk about sulfur now. So sulfur, so there's sulfur conventionally, so we just talk about CO2 solubility, right? So sulfur conventionally is thought, and CO2, let's say, CO2 actually, we know that it degasses pretty early. So this plot, it doesn't have numbers, but we know that the curve more or less look like this. But so basically at high pressure, it already started dropping a lot. But then sulfur, conventionally, we think, okay, it comes out very late. And partially it's affected because most of the experiments are actually between 1 to 2 kilobar. But that's the conventional thought. But then as I mentioned before, as we know more about sulfur speciation, we realize it's actually more complicated. First of all, the concept solubility might not, I guess depending on who you talk to, but it might not super applicable to sulfur, because unlike water and CO2, when it exhausts, it exhausts as water and CO2, right? But then for sulfur, it's different. So we are talking about, so sulfur is a multivalent element. So it can exist as sulfur 6, sulfur 2-, and sulfur 4+, right? That's like the 3 most common valent state. And so when we talk about sulfur in the magma, we're not really talking about the element sulfur. We're talking about sulfate, which sulfur exists 6+, and or sulfide, sulfur exists as 2-. And then when we talk about vapor phase, we're not talking about sulfate and S2- either. We're talking about H2S and SO2. So if in this 2-phase word, sulfur, we're already talking about 4 different kinds of sulfur. And again, if we also include the solid phase, because that's another thing, is sulfur could also exhaust as a solid phase. It does not only go to the vapor. And then we're talking about iron sulfide and some kind of sulfate, most likely calcium sulfate. So it's more complicated here. And so then because of its multivalent nature, then we need to consider a lot more equilibrium, right? We need to consider, what's the equilibrium between sulfate and sulfide in the magma? And what's the equilibrium between H2S and SO2 in the vapor phase only? And then what's the equilibrium between the vapor and the melt regarding sulfur? So for the magma, so this is also kind of new. I think we really started to understanding this since 2010, but it's still kind of, our knowledge is still evolving, and along with the advancement of the like the measurements of the sulfur speciation. So basically, in the magma, there's the equilibrium we need to deal with is the sulfur together with another very abundant multivalent element, which is iron. So we can basically write an equation like this. So sulfide reacts with a ferric ion. So sulfur got oxidized and iron got reduced. So we notice that sulfur is actually a very efficient element in terms of transferring electrons, right? Because from S2- to S6+ is 8 electrons, and that involves 8 moles of ferric and ferrous ion. Again, so basically in the magma, what we know is that really it only exists as sulfate and S2-. And then in the vapor phase, there are actually more other species, but the most abundant ones is H2S and SO2. And then when it reacts with water, that's the reaction we're dealing with. And so now we can already see is, so water fugacity matters, and because there's oxygen and there's oxygen in the and a ferrous ion, so oxygen fugacity of the system matters a lot. And of course, temperature, which is basically a factor of the equilibrium constant. So there's like more players here when we're talking about sulfur already. This figure 8 basically is to show us how sulfur speciation change as oxygen fugacity change. So this oxygen fugacity basically we can look at it as how much iron in the magma. One of the ways of describing it is how much ferric iron in the magma. What's the ferrous iron ratio in the magma? So we can see when it's very reduced. So here, if it's below this, below this 0 on this left side, or between -1 to 1, we're more talking about MORP. And between 0, between 0.1 to maybe 1, we're talking about OIB. And then most arc magmas is actually above 1, FMQ +1. So we can see but this is actually the area most of the tectonic settings include, right? And then sulfur speciation actually changed dramatically in this region. That really affects how sulfur degassing, in different magma. That's why it really matters. We really want to know sulfur speciation. So because of all this, we have a different term to really describe the sulfur behavior during degassing. There are actually many, but then one of the way of doing it is actually using instead of using solubility, we're describing it as partition coefficient. So basically, it's the ratio between the sulfur concentration in the vapor divided by the sulfur concentration in the melt. This concentration can be either weight percent in the vapor and melt, or it can be mole fraction in the vapor and the melt. Just be consistent. If you're using weight percent, then both should be in the vapor and in the melt. And another way to see how complicated sulfur behaves during this really narrow range of oxygen fugacity, that kind of include all the magma settings we're interested in on Earth, is if we look at, so all these symbols are experiment results. We calculated the sulfur partition coefficient. Here is the weight percent, right? The weight percent of sulfur in the fluid divided by weight percent of in the melt. So these are what experiments can tell us, right? If we plot all these experiments, they are actually at different pressure and different temperatures. And along the oxygen fugacity of the experiments, we can see it actually increase and then decrease. So that's like really interesting and complicated because it's not like a one-way effect. So it makes it very difficult to model this sulfur partition coefficient using like a universal equation. So there are different ways of modeling sulfur. One of the way we just said is the partition coefficient, and the classic model here is or like by 2019 is SOLEX. So basically, they have the experiments and they kind of write it out. The experiments do at different pressure, and then they have this like very simple like parameterization, and it's only a function of pressure here. Because and that is because they will only really use one set of experiments to calibrate this. And in these sets of experiments, we can see that the partition coefficient is kind of going down first and then going up. But then later we kind of when I went into this model and the sets of experiments, there are actually several issues involved with the experiments itself. I think that's why like some of the, that's why like SOLEX actually fail in some of the later, like when I try to apply it to like other like magmas that with other conditions. Anyway, so and then there's another way of modeling it apart from using the partition coefficient is to use this kind of fugacity law. And this is by the way, SOLEX is available using a Excel spreadsheet. That's why it's so commonly used, because it's in Excel. And then so decompress is another commonly used degassing model that can actually deal with sulfur degassing. And then what they are using is, again, all these symbols are experimental data. So what they are parameterization is basically the SO2 concentration in the melt, and equals to, A and B are constant, and then the fugacity, the SO2 fugacity and the H2S fugacity in the vapor phase. And that's another way of dealing with sulfur degassing. But again, first of all, this decompress is also really calibrated using like one or two sets of experiments. And second is actually none of these experiments has pressure higher than 200 megapascal. And then the last way of dealing with it is actually using sulfide and sulfate capacity. So what is sulfide and sulfate capacity? It's actually really similar to equilibrium constant. You write this equilibrium, it's actually pretty similar to equilibrium constant. So this is another way. So when you write a equation of sulfur dissolving as sulfide or sulfate, and then you write out the equilibrium constant of the reaction, and you define this kind of term, sulfide and sulfate capacity, and then using experiments to calibrate it. So this is actually used in an old model, Moretti and Papale. This model is, so it's really interesting because this model is rarely used by melting inclusion community, but it's widely used by volcanic gas community. So to infer the degassing depths. And then there are some newer models also adopt this sulfate and sulfide capacity. And you can see they're all after 2000. That's because I think in 2020, there are some new experiments are done, calibrate the sulfate and sulfide capacity. But the problem is, I think most of those new experiments are actually still done at 1 atmosphere. Anyway, so I think in my in the SulfurX paper, I kind of have a summary about the existing model of describing modeling sulfur degassing, but this really needs to be updated because there are a lot more newer models coming out. I'll talk about in the end. Anyway, so here the problem of, so what really motivated me to really develop SulfurX is because these red symbols are melt inclusion data from Fuego 1974 eruption. So as I talked about, one of the post-entrapment modification of melt inclusion is the vapor bubble inside the melt inclusion, and that can really take a lot of CO2. And before, people did not really see it because they just ignore the vapor bubble. But then after, if you redissolve those vapor bubble back into the melt, we can see the melt inclusion contains a lot more CO2. So compared to these gray symbols are basically not counting the vapor bubble. And another thing is really interesting is, so conventionally, we think sulfur degas very late, right? And it's not a problem if we look at the gray symbols. It's basically when the CO2 is already very low, sulfur, you still get 3000 ppm sulfur. But now we corrected for the vapor bubble, all of a sudden, it looks like instead of degassing late, sulfur and the CO2 actually are degassing together now, right? So it looks, so then there's really a co-degassing trend, kind of showing that, oh, sulfur actually is also degassing early here. And then I applied like I think that at that time I applied the available models to these data sets. And none of these models, these dashed lines, can actually predict this co-degassing trend. So that's really like, so the solid line is an empirical model. It's basically an empirical fit. So that's really motivated some of us to say, oh, we want to develop a different sulfur degassing model to describe, can reproduce the melt inclusion data here. So another thing I did is I also compared that this is another figure basically showing that why we need more sulfur degassing model. So here I basically applied again those three models. So we can see to model the water, CO2, and sulfur degassing. So the x is the concentration and the y is the pressure. So we can see it does agree relatively well on water, and these and the blue lines are CO2. So I guess they are different, but they're not very different. And the red lines are sulfur. We can see that they're significantly different. They like even the shape of each model actually looks different. Some models predicts early degassing of sulfur, but others predicts very late degassing of sulfur. So there is a huge discrepancy in predicting sulfur degassing. So now finally come to SulfurX. So SulfurX is actually a model try to predict the evolution of sulfur, CO2, and water degassing in the basaltic and basaltic andesite magma during decompression. So the way it does this is actually employs sulfur partition coefficients and combining the sulfur partition coefficient with the existing CO2 water degassing model. So basically, we first have the CO2 and the water degassing calculated by an existing model, and then I distribute the sulfur between magma and vapor using sulfur partition coefficient. So this model also tracks the redox change, basically predict using like sulfur and iron reaction. And so here is how SulfurX model the sulfur degassing. So basically we wrote, so these are the two reactions. Again, we write reactions first, right? So this is the two degassing reaction we're dealing with. It's the sulfide degas to H2S and sulfate degas to SO2. And then I write equilibrium constant. And so these are all kind of familiar. But we just like one thing I want to say is that the advantage really writing out these equations are by looking at equations, you know what is the major player here, right? So you can see that for reaction 1, water is definitely a player. It matters. And then because we are talking about iron sulfide, that's like the common K-time sulfur sulfide will actually combine with. So iron is definitely a fact. It has a huge effect. And then if we're looking at reaction 2, then water doesn't matter anymore, but oxygen fugacity matters here. Because we are dealing with sulfate, which is S6+ in the melt, degas to SO2, which is actually S4+. It's a redox reaction here. That's why oxygen fugacity also matters. So anyway, so I write out the equilibrium constant, and we can see again pressure, temperature matters. And then for reaction 1, water fugacity matters, and iron concentration in the magma matters. And then it's the H2S fugacity, and then pressure. All right. So for reaction 2 is actually different factors here. Reaction 2, because there are different K-times combining with sulfate. So we consider this basically using again like a kind of different parameters that represent the compositional factors here. So again, you also have pressure, temperature, and oxygen fugacity. So the advantage of considering 2 reactions instead of just 1 is because really for different chemistry reaction, what really matters actually are different. So the way SolveX does it is actually calculates these 2 partition coefficient, and then combine and then calculate a combined partition coefficient by using the sulfur speciation in the magma. So the sulfide over total sulfur times reaction 1. So it's a kind of a weight sum of these 2 partition coefficient. And so this is the key or the difference of how SolveX dealing with sulfur degassing is we are not only looking at 1 partition coefficient where you actually calculate each reaction, 1 partition coefficient for each reaction and then combine it. Yeah, so this basically there's the table basically say, oh, what experiments are used to calibrate SolveX. We can see that it's really, most is the basalt and some basaltic andesites. And it does have some experiments that actually with high alkaline. So it could be used to alkaline basalts, but because this, you can see this really comes from 1 experiment. So I would say I would put caution if I apply SolveX to alkaline or like really high alkaline composition. And here is actually the pressure and the temperature range of the experiments that used for calibrating SolveX. Okay. And this is basically show how each partition coefficient, the predicted versus the measured one in the like used to calibrate each reaction. Okay, so finally, so here's the framework how SolveX would work. So the required input is actually kind of simple. We just need a water, CO2, and sulfur to start with, and then because sulfur is related to oxygen fugacity, we also want an input of the ferrous iron ratio, or it could be a relative oxygen fugacity. Basically, well, what is the FO2 relative to FMQ buffer? And then we want to know the melt composition because that's also used to calculate the KD, and then temperature. So SolveX for now only does it as isothermally, so the temperature doesn't change during the whole degassing process. And so use all these conditions, SolveX would calculate. So another thing is you can see that the pressure is not one of the input here, and that is because SolveX assume the magma start decompression when it's already fluidly saturated. So the way SolveX determine the initial pressure is to use your initial water and CO2. So basically, you always starts with where where your magma, this initial water and CO2 becomes vapor saturated. So that's how SulfurX determines the initial pressure. And then so that's why the next step, it calculates all these initial conditions. Yeah, so the initial pressure and the initial vapor phase. So the very first step, again, it doesn't partition sulfur into it. It really just uses the water and CO2 to calculate the saturation pressure and what's the vapor composition. So it's really just water and CO2. But then in the magma, you calculate the sulfate over total sulfur ratio using the ferric ferrous iron ratio. And then using the ferric ferrous iron ratio, you can also calculate the initial FO2. And then that's how you have the very first step. Everything is ready. And then SulfurX can decompress, can start decompression. So this will decompress all the way to 1 atmosphere. But you can actually assume how big the decompression step you want by changing one of the parameters, basically like how many steps you want to do. For example, if you want from 300 megapascal to 1 atmosphere, if you say I only want 10 steps, then that's really big. And I think that wouldn't work. I think SulfurX wants to deal with very small steps. So usually I would say I would usually use like 300 steps and something like that. But it really takes very short time to calculate. So so then when decompression starts, so it will drop a little bit pressure. And then at this time, sulfur starts to partition into the vapor phase. And then the way it decides is to first calculate the KD, KD for reaction 1 and reaction 2, and then the combined KD. And all these will be calculated using the previous step, right? All the conditions from the previous step. That's why the pressure step needs to be very small. So basically, like everything barely changed. That's why, and this is especially important when you actually want to also track the FO2 change. Otherwise, it will be very difficult to find a good solution. So then it also calculates the sulfate ratio, SO2 over total sulfur ratio in the vapor. And then using all this information, so basically SulfurX would solve. So this is like the main degassing part, would solve all this equation together. So for water, if we remember, we just look at like water concentration is a function of pressure and also the vapor phase in the partial pressure of water, right? And then CO2 is CO2 in the magma, and then it's a function of partial pressure of CO2 in the vapor. And then there's the mass balance. Oh, by the way, so the available version on my GitHub and also on Victor, it only deals with the closed degassing. So we're talking about everything maintains closed from high pressure to low pressure. And then there is the mass. There is we also assume, or we only assume there are only 4 components in the vapor phase: is water, CO2, and SO2 and H2S. All these will add it up to 1. And then we also have like the mass balance of water, a mass conservation of water. So water only partition between melt and the vapor, and mass conservation of CO2. And this is another equation. So these two, you can write more equations here. And then you can decide if you want to deal with crystallization or not. If it's only if you only want to run a fixed composition, then the crystal, the mass fraction of crystal will be 0. And then we are only dealing with mass fraction of melt and mass fraction of vapor. And this is also conserved. And then we also have the sulfur conservation here, basically using the KDs. So SulfurX would solve everything together. Again, some of the inputs will be using previous steps. That's why we want to use a very small step. So otherwise, it would be difficult to solve all these equations together, and it cannot find a solution. So then here we say, okay, we don't want to track the FO2. Then the FO2 would stays the same. Basically, the ferric ferrous iron ratio in the magma doesn't change. And then after it calculates everything, so what it calculates is water, CO2, sulfur in the melt, concentration in the melt SO2 and H2S in the vapor phase, and also the mass fraction of vapor, mass fraction of melt, and mass fraction of crystal if you allow crystallization. And then it will update everything and then goes to the next cycle. So then the pressure drops a little bit more, and then it's continue doing this until 1 atmosphere. So that's how like the basic idea here. Any question? No? Okay, cool. I guess I won't go into too much, but what SulfurX can also do is actually because sulfur is a multivalent element, right? When it degas, it actually causes some electron exchange in the magma and in the vapor phase, and that actually changed the redox of the whole system. So SulfurX can also predict this, and then this involves solving these 4 equations together. So basically, we are dealing with the dealing with the equilibrium between sulfur and iron in the magma, and then the ferrous iron and oxygen equilibrium is this one, and then H2S, O2, and SO2 and water equilibrium in the vapor phase. And then the last equation, which ties everything together, is this redox budget conservation. So basically, we assume there's the whole system is a closed system. So the amount of electrons that are available compared to certain reference states is always the same. So these are 4 equations, and we have 4 unknowns. So SulfurX can actually, again, solve all these 4 together and find an FO2 that satisfies all these equilibriums. So that's how SulfurX deals with the redox change of the system. So then if we want, so what we just went through is actually this half, this lower half. If we don't think we don't want to know how FO2 change, but if we do want to know how FO2 change, is after this cell D, it kind of calculate everything a little bit. So if we want to find an FO2 after partition, there is a certain amount of sulfur partition into the vapor, what it does is it will enter a new loop. And this loop basically will use the FO2 from the previous step, and then to try, if this FO2 satisfy these 4 equations, okay? And by satisfy mean if the solution actually compared to so the loop will run multiple times, right? Each time it will solve for a FO2, and then that solved FO2 will be compared to the previous FO2. If it actually stopped changing or smaller than a certain threshold that you tell SulfurX, that means, okay, I assume if it's very small, then I assume it doesn't change anymore, and then I can go to the next pressure step. But if the FO2 change is actually still pretty big, by keep solving this solution, then it will just enter the next round. So until it finds until the FO2 actually stop changing. So if you actually also enable the tracking the FO2, this would actually takes a little bit longer, but not significantly longer. But it could also sometimes there will be excursions for finding the common FO2, and so there are a few parameters you could actually adjust to minimize that kind of excursion. Okay, and one last thing is about, before we go to the Victor, is about how SulfurX deals with the crystallization. So this is a little bit empirical, I would say, because SulfurX itself does not really calculate how magma crystallize and how magma composition would change as crystallization goes. So this actually really needs you to input. So the format to input is actually we want so there is a place you can input how different oxides change as a function of the melt fraction. And how do you get this information? If you know, like if you have a lot of melt inclusions, you can know how SiO2 change as a function of melt fraction, how iron change as a function of melt fraction. You could input this kind of information in SoftX, but SoftX itself doesn't really calculate that. Another way to do it is you could also simultaneously, you could run some of the, the crystallization model, for example, magma set in Anki or Petrolog, all those models can deal with the crystallization, and it can tell you how does each oxide change as a function of melt fraction. And then you can input that kind of information in SoftX. So SoftX, because SoftX does calculate the F, right, the melt fraction, so it will change the major element composition using the information it tells you. So one key thing, you want to link the degassing with the crystallization, and which is also an input of SoftX, is this water and potassium oxides relationship. So why potassium? So potassium is assumed to be a full, perfect incompatible elements here. So basically, it's actually, we can basically assume potassium concentration is basically 1 over the melt fraction. So that means it's perfectly incompatible. So in that way, you could actually put another constraint about the water concentration and the melt fraction here, right? So this kind of, it's also kind of empirical, the potassium versus water. So for example, this is an example for Fuego. If we only look at this zigzag line, that really describe how potassium and water change as the function of crystallization. And so we do want to know this part in order to take into in order to enable the crystallization for SoftX. So basically, it's the melt composition change as a function of melt fraction, and particularly how and also how potassium changes as a function of water. Yeah, I mean, I guess not all the not everyone would have that kind of a full sets of the melt inclusion to give this information. So another way to do it is to use another model to kind of predict, like for example, the magma set or Petrolog. Okay, yeah, I guess what I want to kind of emphasize is so what this SoftX paper or SoftX kind of do is calculate 2 different KD. This is a kind of a summary of SoftX. Calculate 2 different kind of KD and then combine it, and then calculate a combined KD. So we can see that this backline is the combined KD. It kind of goes through the trend that the experimental constraint KD shows. And what really helped, like kind of showed us, and is really important, is that so the conventional thing, we thought sulfur degassing is basically this dark green line. It's like it does not degas until the last 50 megapascal. But but then what SoftX kind of indicated is that it does not really have to be the case. It depending on the 2 most important factors here is one, sulfur speciation. So here the green sets are the sulfate, very little sulfate. There's only 10% sulfate, and the kind of the yellowish sets is you have a lot of sulfate, which is more likely to appear in magma, arc magmas, and this one is more like warp or ocean island basalt. But that's one important player is the sulfur speciation in the magma. Another important player is actually the water concentration. Remember, for reaction 1, water is actually in the reaction, right? That matters, that affects. So if it's a very dry magma, sulfur tend to degassing late. So for example, this dark green line is basically very little sulfate, mostly sulfide, and then dry. So it does not degas until very late. But if the magma have a lot of sulfate and it's wet, then we can see sulfur could actually degas pretty early, right? For example, this one with 4.58% water. I mean, it's not super wet. Thinking about the arc magma, it's pretty normal. It actually degas pretty early. It starts degassing, at a pressure higher than 300 megapascal or even 400 megapascal. So these are the 2 important players for sulfur degassing. It's the sulfur speciation and the water concentration of the magma. Yeah, so then the application, one common application is to calculate how much sulfur could be degassed. Again, if it's a wet oxidized magma, it starts degassing very early, and a lot of sulfur can be degassed. And if it's a very dry magma and it's reduced, it only degasses like really shallow place. In that case, you might not have a lot of sulfur degassing, particularly apply to submarine volcanoes because the eruption pressure is actually pretty high. Another application again is to calculate how redox of the magma could change along degassing. For example, this is an example. All these purple symbols are from our melt inclusion data, are actually glass data from Mauna Kea, right? So we can see that really the ferrous iron ratio in the melt actually decrease. There's a redox change along degassing, and we can also use it to interpret the CO2 sulfur ratio in the volcanic gases. Basically, okay, what pressure does this CO2 sulfur ratio in the gas? Does this gas come from with a relatively low CO2 sulfur ratio? And what pressure, where does the gas come from if the gas ratio is actually really high? And this is particularly interesting for some of the volcano that actually has a lower ratio during quiescent degassing, but then it has really high ratio in the gases that comes out a few weeks before eruptions. So this is another application. So this is one of the output of SulfurX. So this is the predicted sulfur CO2 sulfur ratio in the vapor. So it does not only predict the CO2 sulfur in the magma, but also in the vapor phase. So then we can compare this ratio to the volcanic gases to infer where does the gas come from. I guess, yeah. So I guess the last thing I'm kind of also interested in is, again, what we all talk about is the equilibrium situation, but it does not really have to be the case, right? So it depends on the ascent rate and depending on the diffusivity of the different volatiles. But in this case, sulfur, the equilibrium situation can be also implemented into bubble growth model to really look at this kinetic case. That's another potential application myself is actually really interested in. Okay. So I guess that's it. We can go to solve the demonstration now, if I can click this. And so I already have this open. Can everyone see it? So I already opened it through the terminal, and then this is the SulfurX workflow. So well, yeah, so then we can see that these are the basic inputs here. The temperature, again, SulfurX runs it isothermally, and then different input of oxygen fugacity. Here, required input is actually relative to FMQ buffer, initial water, CO2, and the sulfur. And then, so there are a lot of like 1 and 0 question. Basically, 1 means enable, 0 means disable. So if we disable crystallization, then the melt composition would stay the same. And if I say 1, then you will take into account crystallization. And here is the total steps. So this is where you decide how small the steps should be. And then M is actually the number of the steps you want to run. So if you don't really want to run to 1 atmosphere, this number can be smaller than L, but it shouldn't be bigger than L. And then because SulfurX runs connecting a CO2 water degassing model, so here we have two models to choose. One is volatile calc, is a relatively early model. I guess one should only use volatile calc is a very dry system. Like if you want to look at like Mord or maybe Ocean Island basalt. And 0 is Incono-Marziano model that more applicable to arc magma. And then this sulfur iron choice is basically you choose a model to describe the equilibrium between sulfur and iron. And there are actually 4 options. So there's there 0, 1, and 100 are like 3 existing model. But because we are actually really our understanding of this equilibrium is still kind of updating. So there is another choice is you can put another like a modified using a modified version. So basically put a different number, a number different than 0, 1, 100. What it does is actually you are going to modify this Moose model to fit your own data. And I would only recommend you do that if you really have your own data sets. Basically, if you actually measure the sulfur speciation and iron speciation in the melt, and they change, and the trend it displayed does not fit of any of this model, then you can use that modification version to actually fit on in your own data sets. And then you have the FO2 tracker or not. If you want to track it, you can have one. You input 1. If you don't, then 0. So what I usually would recommend is even if you want to track FO2, I would disable this one first. So I would always run a degassing trend without tracking FO2, because again, then remember the way it tracks FO2 is actually it enters another loop, and then so we want to find the baseline to see all the other things work well, and then you can turn this on to track the FO2. And here you also have like if you want to, in the end, you want to plot your melt inclusion to be compared with your model, you can upload your file here, I guess. Yeah, you can upload the file to the source file, I think, and then save it. And then in that way, it will read that file and change the name here, and then it will read the file so it can be plotted in the end. And then output file. So here you can change your output file name. And there's a save image. Okay, it saves true. I guess that just saved the image. Okay, so the next cell is really about how do Sulfur estimate the errors, the predicted errors. So the main source of error it considered is actually the Sulfur partition coefficients. So the way it does it is so using like it runs Monte Carlo simulations. So it will run so the KD, when it calculates the partition coefficients, there is a arrow, or there's a range coming from the KD calibration and the calculation. And then after calculate that, if you enable this Monte Carlo simulation, what it will do is at each step when it calculates KD, it does not use the KD that calculates, but it chooses a random number within the arrow range of each KD. And then it will just keep running. So that's one run. And then you can tell it to run a lot of runs, like 500 or 1,000 runs. That will take a while. But yeah, so in that way, it will output, the output of sulfur and CO2 sulfur ratio in the vapor would be a range instead of a, one number. And that's how SulfurX estimate the error. And if that's the case, there is a separate output file of what's the sulfur of each run, each Monte Carlo simulation, and what's the average and what's the standard deviation of that. And there's another output file for CO2 sulfur ratio in the vapor. I mean, you can write out more if you are interested in other, but what really the arrow account for is the estimate of sulfur error here. And here, this one is, so this, I think the melt fraction is the starting melt fraction. It always starts with 1. And then this incremental and the bar is, this is basically because, so SulfurX is more likely to give all those big excursions at a very low pressure. The reason is because there is a huge difference of the KD constrained at 1 atmosphere and the high pressure experiments. So there will be a lot more sulfur coming out at the last few, at the very end of the degassing, close to the surface. So sometimes it does not, you could not find a conversion. And sometimes it might be actually the predicted KD can get like really, really large. So that your degassing model might not run to the surface. In this case, you could actually tell it, okay, the bar basically, you can tell it is at a below certain pressure, you don't want to use the calculated KD, but you want to increase the KD as a arbitrary number. So the incremental would be this. So this INC is how many arbitrary number you want to increase. Okay, here it says I want to increase by 20. And the bar is basically at what pressure you want to do that. You can say I want to the last 10 bar because it doesn't converge. So I'm gonna, instead of calculating a really large KD and have problems, I just want to increase by 20. This is more likely to happen when you enable the FO2, because the FO2 will affect the KD. And if the FO2 all of a sudden has a large excursion, and then the KD will have a large excursion, and then everything can blow up. But usually, if you don't want to track FO2, I think there shouldn't be any problem running to one atmosphere. And also, I would recommend if you use this function, you want to really compare by 1 atmosphere, what is your KD? You want to check that, and if it's reasonable. I think from like the volcanic gas and the glass study, that number for sulfur, that number should be should be around 1,000, and I think that's like kind of reasonable. So if it's not like that, you know, you could also, based on that, you can decide what's your increment level too. And then this one is the sulfide phase. So there is I guess one thing SolveX doesn't deal with right now is what if it crystallized sulfide or sulfate. But it does kind of calculate what would be the solubility of the sulfide and sulfate. Basically, like, okay, how much sulfur should be in the should be in the magma before it crystallizes sulfide and sulfate. So this kind of calculates, and then you can kind of compare, and this would be also in the output file. So you can kind of compare to get a sense if your magma actually reached sulfide or sulfate solubility. So this would be one of the things I would like to work on, like implement in the future, is to really take into account the sulfide saturation. Because I think it's at least like for more some ocean island basalt, that is the case. People have seen sulfide in the magma. Okay, so then next one is the sigma. This sigma is the tolerant we just talked about when, then this is only relevant if you enable the FO2 tracking. So this would be like the tolerance of the log FO2. So basically, when you try to find the FO2 satisfying all the conditions, you calculate one, and then you compare your calculated one with the previous one. If the difference is actually smaller than this tolerant, you are assuming the FO2 stop changing. So this one is actually pretty important you can play with it, and when you want to track FO2 to make sure it finds the correct answer without go too far. Because if it's too big, it might not track the right, it might not find the right FO2. But if it's too small, it will make it really difficult to find the solution. So you can, if you have problem and have big excursion, when you run FO2, you can actually play with this one to see, that could actually improve your run. And then this slope. So basically, these two is describing. I think here it says pretty well. This is how you use it to describe the water and potassium relationship. This is another empirical input. Yeah, but this is only relevant if you want to also take into account of the crystallization. I think so. These are all the things, but I guess there's another input which is not in this workflow, but you can still change. Is the melt composition. So I think what you want to do is you go to this source file folder, and you have the melt composition. So this is a little bit more complicated, but what you want to do is if choice equals to 1, basically if you want to crystallization, then again, as I said, you want to say, okay, how does the each oxides change as a function of melt fraction here? So here is basically all so here you can change whatever shape you can do. You can just use the existing format, or you can enter your own. And here it gave you a threshold, basically say, okay, when the melt fraction is smaller than a certain time, you stop changing the melt composition. And if you don't want to melt composition to change, then you change the melt composition here. So this else. So this would be your initial melt composition, and it will stay almost the same. Why almost? Because your melt fraction is going to be still changed, and then that will always recalibrate that. The melt fraction still change because you will start making vapor phase, right? So the melt fraction still getting a little bit smaller. So that will be the only change here. So that's how you can change the melt composition. It's a little bit inconvenient for now. I'm still thinking about a better way to implement this. But yeah, so that's how you can change the melt composition. Okay, so I think that's all. So you can just run everything, and I think if you just do this, I guess. So it will run. It's really scary. I think this has something to do with how I code like using the pandas, but this is not really an error message, and I will fix that later. But in the end, it will make this figure. So basically, you can also try to change what figure you want to plot. If you go to the main function, this is all at the bottom. So here, what I wrote here is really to reproduce all the figures that was published in the Sulfur X paper, the G-cube paper. But you can change, yeah, I guess that is probably everything. Any question?
Iko, can you show us how the CSV files looks like?
Oh, yes,
for the input.
Right.
Yeah, these are the outputs, right? So that's what you get at the end once you run it. But you mentioned that you can use some CSV file as inputs.
Oh, as the input.
Yeah.
So I think the CSV file, I don't think here it plots because the CSV file, I think the inputs you get for the model itself, you just change it here. The only thing you could do is you can upload this melt inclusion file, and then later you can plot it. I think all you need to do is just to upload the file, but that's only really for plotting. It's not for the model input.
And does it have to have a particular format, or
you mean the yes, it's like this.
Oh yeah, here we go. Yeah, okay.
Wait, this is right, but I guess this part is really for plotting. You could just change this file. I think it's on my GitHub. But you could also just change here. What do you really want to plot with?
Okay.
It's pretty flexible. But I guess one more thing I could go through is the results file, because it does produce a results file, and this is all your results. So the name, you can change it in the workflow, I think. Yeah, so this is the output file, and this is the results. So pressure, this is in megapascal. And then you have, I think what you do people really care is the weight percent. This is the weight percent in ppm. Weight mass fraction in ppm for sulfur, weight percent for water, and ppm for CO2 in the magma. And it also outputs the molar fraction of different volatiles. This is the total sulfur. This is the water, CO2, SO2, H2S in the fluid. That's the output. It's in molar fraction. That's why it's X, I guess. And then there's a fugacity coefficient, just in case it's interested. And then you have the weight percent sulfur in the fluid. This is W. And then you have the mass fraction, melt mass fraction, vapor fraction, and crystal fraction, because we just ran it, disabled the crystallization, so it's always 0. And then there's different KDs it actually calculated. And then SO2 sulfur in the vapor and sulfate over total sulfur in the melt. So there are a lot of I think what really important for most people is the concentration of water, CO2, sulfur in the magma, and the mole fraction of CO2 sulfur and the water in the vapor phase. And then I think there's one more, it would be the FO2. Yeah, the FMQ. And this is really calculated FMQ. What's the FO2 for the FMQ buffer? And then the FO2 itself is calculated here. And then you also have the the sulfide saturation value and the sulfate saturation value that you could compare to. So these are the results file. What else? Any other questions or?
Yes, I have one question.
Sure.
Could you explain again on the set melt fraction and low pressure parameters?
Sorry?
Could you explain again about the set melt fraction and the low pressure parameter? What's the meaning of ENC and BR? Because I didn't understand.
This one, right?
Yes.
Yeah. So what this does is this is not necessary for everyone. I would say would only recommend when after you adjust all the other things. For example, the step of the whole run, the step size of the run, and also the sigma. And then you still it's still kind of sometimes it gives you this big out excursion, like it does not go to the bottom like this. It could actually kind of have a big excursion out, and after adjust. Usually this can be addressed if you adjust the pressure step and the sigma. But if even that doesn't fix the problem, what you could do is instead of having it calculate, right, this KD1 and KD2. So these are basically KD1 and KD2, these two, the blue and orange line. So instead of having it calculate at the bottom, what you can do is you can give it a arbitrary number to basically compare to the previous step of your KD. Yeah, you just give it an increase of a KD. You can say, okay, I want to increase by 50 every step. So in that way, the KD will be, then you make sure the KD is not very crazy, let's say at the bottom. So then in that way, you could actually round around too smoothly. And that's what the INC is. It's basically how much you want to increase your KD. Does that make sense? And the bar is basically, you only want to do this for the low pressure because usually that's where it gives you this kind of problem. So the bar is actually in bar. So it's below what pressure you want to start this arbitrary increase of your KD, of your partition coefficient. Instead of using the calculated one, you use the arbitrary increased KD. So you can say last 10 bars, or last 50 bars, or last 5 bars. So yeah, does that make sense?
Yeah, now it makes sense. Thank you.
Yeah, thanks.
I have a question.
Sure.
Have you thought about combining the outputs from these calculations with, for example, calculations for viscosity and other thermal properties like thermal diffusivity and things like that then can be maybe put into a conduit model?
Yes. Yeah, that's I'm actually super interested in that. That's my next step. I do want to combine this because as I said, this only addressed the equilibrium situation. So we want to know when it's not equilibrium, how does everything works, and especially if that affects the gas composition. That's actually what I'm kind of interested in. Yeah, so yeah, I think that's my next step.
Cool.
Yeah.
Is there any other questions for Eiko?
So then maybe I missed it in the beginning. Did you mention about the final projects and presentations? at the end?
Well, I kind of actually said that yeah, students could present their project, especially how they want to use Victor, if they want to use Victor for their project. Would be good to do a presentation, yeah, during the 2 last weeks. And then the fact that we could also give them a little activity to do for these 2 last weeks, could be like a code to run through a workflow, and then they can actually try to get some output and compare some outputs. So yeah, I think we should probably talk about that again after spring break, and then try to get a plan for these last 2 weeks. So if you guys can email me if you're interested in doing something during these last 2 weeks, please email me with just a little sentence saying that if you want to present your project, or if you prefer doing something that we gave you, and then we can gather all these and organize these 2 last sessions in the end of April. Yeah.
Okay.
All right. No other questions or comments? Okay. I'm gonna stop the recording. I thank you very much, Echo.